actions, the signals.
Yeah.
I flushed it.
You also have the MT2 out, right?
Yeah, it was look at the. Oh,
Well, you actually like the unredacted one.
Well, the redacted one, you can literally just download the picture on your phone and you just get the thing. That's what I like. I was like
you can take away the.
Well, you can just like if I go if I went to the assignment, I can just click I can just hold the picture and just save picture, and then the photos just part of it.
Oh.
Yeah.
Oh, that's fun. So you could literally just copy and paste the pictures.
Well, redactions are all applied on top of the image. Yeah, they're not actually on there.
Yeah.
So theoretically, I did it on my phone. I don't know if it it's probably worth. I think I would be able to. It's probably just a little more inspect elements. Yeah, I'm not really sure.
I think that could be messing something up.
But I mean, some of them are kind of obvious.
Yeah.
And generally, if you get the right shape,
and with the having the redacted one and all the
yeah, I mean, my
I mean, he said you can do that, so it's
Yeah, but I do. Or if you don't, then
Okay, guys, we have attendance 1102. It's attendance code. Don't forget to do that. Let's get it started. Okay, first, how was the midterm? Was okay? So? Okay. We're gonna, I think T Nintendo already marked that. It was fast. Yeah, I like that. But if you have any issues, just email me or email her, and you can take a look. Okay, what we want to do for this week? We are in designing processor. Today I'm gonna tell you a little bit how you can use Verilog, hardware description language, to explain CPU or processor. And for your next assignment or project, we supposed to use Verilog to design a very simple single cycle processor. Today I'm gonna cover part of that, so the rest you can do by yourself. Okay, let's get started. So we started introduction last class about processor design, and today we're gonna go more deeper, talk about other part of processor with more details. Last class, I think we covered the data flow in the processor from instruction memory to data memory. So normally, what's happening in normal processor is that we have a instruction memory. Instruction memory is a place outside of CPU actually. But for your assignment, you can consider that even inside. We're going to see some example today. Anyway, this instruction memory is supposed to keep the program in a machine language, like 0 and 1 there. And each instruction we consider one word, 32 bits. And the pointer to the instruction that needs to get executed is specified with program counter. So based on this program counter, we are accessing to one of those instructions. We fetch that, and after fetching, we put that in another register called instruction register. I'm going to put that vertically, but this is, you can imagine, it has different fields. That's instruction register. So it has different fields, like opcode, for example. It has opcode. It has register source, register destination 1, register destination 2, immediate, depends on the instruction. It has different fields. So we fetch, we put instruction in this instruction register, then we decode these bits. Decoding means you are checking to see which instruction is that, which registers you are supposed to read or write. And there is a control unit that's supposed to access to this information and make some signals. We call them control signals. We didn't show that in this diagram, but we're going to see that later. So instruction going to get fetched, registers file need to get access. You can read that. That's still part of decoding. After decoding, you know which registers you are accessing and put the bits corresponding to those. Like this, register numbers, 5 bits in. 2 of them is for reading, and 1 of them is for actually address of writing. 5 bits because we have 32 registers. We specify, for example, we are working with register source, one of them, and these 2 register destination going to go in these 2 to specify which registers we are supposed to operate and make a result. And this is decoding. When we put this information in these inputs, reading register file, this is register file. It has lots of registers, register file, we call it register file. Reading register file is combinational. It's combinational means it doesn't need clock. When you put address here, it can read. So later we're going to see that this register file is a double reader. You put 2 address and at the same time can read two registers and put them in an output. This is output, register out. What I can write in this top? How many bits is this output? Imagine we are using RISC-V, that registers are 64. So when it's 64, of course, they supposed to be 64. So we have 64 bits output. And the ALU do execution. So the next part is ALU performs computation. So ALU do operation, for example, addition, subtraction, whatever we are supposed to do, and make one output. This output can be an address for memory, or can be just the output that we need to write that back. So the last part, okay, if that's a memory instruction, we need to access memory. Again, accessing memory, reading memory is like combinational as well. We don't need clock for that. And when we access memory, we put address here, and the data gonna get ready here as output. When you want to write something, you need to make data. Data is a part of actually registers and probably something else like an immediate gonna add here. We didn't make that so complex. We just put something here, but here we have some actually extra circuits for that. Anyway, we have data ready if it's memory, and make address ready, and then clock coming, and writing need clock. Because writing going to change the state. We always need clock for that. And if it's register or R type, the output going to get ready here in a data. It's going to get ready. I didn't say it's going to written. It's just ready to clock coming. So the last part is a written back. Written back means the result going to put inside or written inside the register file as output. So when the clock coming, this gonna go, and we add 4 numbers, 4 value to the program counter to go to the next instruction, because each instruction is 4 bytes. And we consider that memory is byte addressable. Okay, sometimes not. In this design that I'm going to show you later, we can make it word addressable. Doesn't matter. It depends on your design. Okay, any question about this data path? This is, yes. Oh, this part, yeah, I didn't explain that. Yes, this is for jumping. So sometimes we have jump and branch, and we use this part. And sometimes we're just going to go to the next instruction that we added to 4. But here is not right. So anybody can tell me what we need to add here? Can we connect 2 cables like that together? It's not possible. We need to put something there. What do you think we need to put there? Multiplexer, yeah. We need to put multiplexer there, and program and actually controller to make those signals. Yeah, we're going to see that next in a couple of slides after. Thank you. Yeah, that's right. Yeah, those 2 adders, one is for going to the next instruction. The other one is for jump. As you can see, based on this opcode, we can understand, oh, this is a jump. So, and this is jump PC relative. We are using PC and use some of this information here, like immediate values, and add them together to find the place that we want to jump. Yeah, we're going to see that soon. Okay, so here we want to see if we want to design a processor using Verilog, what steps we need to do. First of all, are you guys all familiar to Verilog? Anybody not heard about that in this class? We all know last semester, the people that had class with me, I think in the lab you learn a lot. But if you don't, you can go take a look. But for this project, I allow you to use AI. That's fine. You can, as far as you understand what's happening, you are okay to use AI to generate code for you. But I want you to run it. That's you need to find. Yeah, I can introduce some like online simulator for that, but you need to run it and show that it's working. But you need to understand too, because I'm going to ask you some questions about it. Anyway, so Verilog is actually hardware description language that explain the hardware. You need to, for making a circuit, you need to have 2. You need to have one design part, one test part. That here we're going to see how we can make that in a very general, like a top view. We can talk about that in general, but in details, you can do that for your assignment, next assignment. Okay, so what we're gonna do? We're gonna do all these steps: instruction fetch, instruction decode that we explained last class. So instruction fetch, obtain instruction from program memory or instruction memory based on program counter, and decode it. Decode means take out all parts related to instruction, like opcode, instruction, the register destination, register sources, and some other fields like 7-bit extra opcode, immediate values, and whatever we need. And then we also need to access register files, because we already know register sources. And register sources, you just can put the address over there that is 5 bits, and the output is ready in a register file output to do operation. So, and the next step is execution. Execution is just ILU, and ILU you're going to do operation that you want to do. For example, in this example that I'm going to show you, we are just doing add as a register type instructions, but we're going to do also memory write and also immediate instructions. So execution is just ILU. So perform arithmetic logic operations. We're going to talk about ILU today as well. If we have memory access like write and store instructions, we need to access memory and or write to memory. And the final part is write back. Write back means we put the result in the register at the end, and when the clock coming, writing gonna get finished, gonna settle, store result in a destination, and then go to the next instruction at program counter for next instruction. Sometimes it's a next instruction, sometimes it's jump, so you're gonna jump to a new instruction. So the part that I'm explaining in this part is related to a design part. So the design part is something that explains the processor. The test part is the stuff that you're going to put in a memory. Like, for example, you put the program counter something, you put actually memory, some instructions in memory. Instructions are all binary based on the design that you had. You're just going to make those binary, like for add, for subtract, for immediate add, for example, you have different opcodes, and put those like in fields and make instructions and put them in a memory. I didn't put that in this code. I'm just going to show you that part. You can do that by yourself for your next assignment. You can see that. Anyway, let's explain this, what's going on here. First of all, this is, I'm going to ask you, is this design sequential or combinational? You can see from the code, the beginning, that always and. Is it sequential or combinational? Sequential. Why? Because that clock, yes. For combinational, we just put a star. So this means this is sequential. However, some part of that doesn't need to. Anyway, when everything in this between gonna get executed in one clock. That's why it's a single clock design. Okay, so the first part is the fetch. Okay, in this computer, instruction memory is address, is word addressed actually. Because it's word address, you need to divide program counter by 4 to find the instruction address. So to read instructions. So this makes the address. We access this memory. So in top of this, we have lots of other initialization that I didn't cover that. Like, for example, this is the memory. This is the memory. It's like we define it somewhere in top of this, something like that. This, for example, we have register. We consider 31 to 0. That's why I'm saying this is word address, and we call it iMemory. iMemory. This is part of the assignment that you're supposed to do. That's why I don't write it completely. You need to go figure it out by yourself too. So something like that. So this instruction memory is actually, we define this memory here in top of that. So this is part of, it's not another process, like another chip outside of controller, is inside that. Anyway, so we define that word addressable, as you can see, is a register, 32 bits, and the name is imem. How many? 124 is the maximum size of the memory. It's enough for our design. Okay, so that's the size. And program counter is also another register that already designed. And a program counter is just 32-bit registers. It's not an array, just 32 bits. Okay, so, and who put these values in program counter? In the test code. When you do simulation, you have one test, one design. This is part of design. In the test code, you put, for example, program counter 100, something. So, and put instructions in the 100, 104, 108, and so forth. Okay, so that's why we divide it by 4. When we shift it to write 2 bits, we are dividing that by 4. Okay, that's the fetch part. Any question about fetch? Yes. 1023, because we want to have this much memory. What do you mean? Oh, I don't know. Maybe I made a mistake. This is what I wrote here, but maybe I don't know. I don't know, but the thing that I have is like, I think this is correct because I executed that, but I don't know. Any idea? I'm not so good in Verilog too. I'm not expert in. And but the code that I have is I already executed, and that's like this. I don't know. But I can figure. But this is correct. This is correct. But if it's not, it's fine. Yes.
I just looked it up. The first number is supposed to be the most significant bit, and the last number is supposed to be the last significant bit.
Oh.
Verilog. So I don't know if that.
Most significant bit, but that's just an array. Yeah, what this gonna make is gonna make us something like that. Okay, so this is 1204. Each of these is 32 bits. Yeah, this is most significant bit. This is the least significant bit. Yeah, this is what you say. Yeah. Yeah, for each of these. But for that array, yeah, this is a specified most significant and less significant, but this is just array. That's why it's from 0 to 100. Yeah, I think this is correct. But if it's not, you can see how is your program works. That's not important. But good to ask. Yes, so this is the memory that we have. Any question? Any more question about fetch? So fetch is just access instruction. Right now in instruction, we have 32 bits that has different parts, like instruction, like destination register, sources registers, opcode, immediate values that we're going to access in decode. Next step is the decode. As you can see, in instruction, we start the first 7 bits is the opcode that specifies the type of the instruction. We have register data register. So this format is exactly similar to the RISC-V format instructions. We didn't change that. But we also have function 7. This function 7 gonna help to this opcode for different instructions in a one type. For example, in type R, type registers, if you want to have add, you need to put something in this function 7. They are all part of the instruction. This is for this part, identify instruction fields and identify registers. And then we also can access registers. Register is another memory. This register is a register file, another memory. Somewhere in the top, you also need to define the same way. Register 31, 0. We consider here 32 bits register, but you can consider 64. Whatever you design, you can change it. But here I consider 32 bits. These register files, we have 32 of them as well. We have 32 registers that each of them also are 32 bits. This is most significant and this is less significant bit, of course. And that's just the array of them. So this is another like a block of memory that is instruction memory. Register file. We also have this. So what we are doing here, we access that register file. We access that register file with this, and we have our source, 2 sources. We read them. This read data 1 and read data 2. This is what coming out from the register. You remember in that data path, we considered register source 1, register source 2, register destination, and 2 outputs. This register is dual, dual register or double? Yeah, I'm not sure. I wrote it somewhere. Yeah, I think dual memory. Yeah, we can see that. This is the dual reader. So it means at the same time can read 2, but in simulation, we can't make that. We're just gonna access to these registers, this type of memory that we created as a register file, and access them and read them as an output. Those outputs are actually register data 1, or I'm sorry, read data 1 and read data 2. So this is decode part. Any question about decoding? So it has 2 parts. Not just we do decoding, also we're reading too, because reading doesn't need clock too. You know, just whatever you put as an address, the output gonna get ready right away. You don't need to wait for edge of the clock. What about immediate? Immediate is also considered part of instruction. For immediate instructions, we in the same instruction we consider 12 bits. 12 bits from 20 to 31 as an immediate value, but it is sign value. So how we can keep the sign? We need to extend the sign. Anybody can tell me what this part means? 20 instruction 31. Sorry? Yeah, this is most significant bit. That is the sign, and we just fill 20 bits with this, the rest of the register. We have 32. We use 12 of these here, and the rest is, as I mentioned, we are extending the sign. Whatever sign was, if it was negative number, it's all gonna get 1. If it's positive, it's gonna be 0. We are extending the sign using this in Verilog. Okay, any question? Perfect. So we have fetch and decode. Let's go to execution. In execution, we just have that for add, but we can add whatever you want. But we need to know some extra information to understand this. So first execution is coming from opcode. Okay, we already know what is opcode, because finding opcode was part of instruction decoding. So we have already opcode. We also have some parameters and that we already know. For example, we know R type. In top of that, we also define some parameters or some initialization. That parameters, for example, we put for R type a value like 7 bits, binary 0, 1, 1, 0, 0, 1, 1, something like that. So this is for R type. We define those variables in top of that. So we already know what is I type. Also for LW, for load word. Also for R type. This is I type, that for I type. So we already defined those. So you know them. Okay, so they are known. Okay, and when we are here, we are doing a case in Verilog based on opcode. We're gonna do some of this. If it's R type, we do another case, because R type has also another opcode that is function 7, because the opcode showing the type and function 7 showing which instruction in that type. So for example, for add, we consider 0. You can add other instruction. In this, we just put add. So if this is add, we add to register data, to read data, sorry, and put the result in ILU result as another register. We already defined all of these registers in top. If it's not a function, if this case is not true, if the function is something else, we put it 0. That's for R type. If the opcode is I type, because for I type we just want to do one instruction, we don't have another case. Okay, we just use one immediate data, immediate values that we are already found that from the last part, and read data that also we have that from opcode, from decode, add them together, put them in ILU result. So ILU result can be adding these two, can be adding this with immediate, or it can be from the load. If it's from the load, we need to make an address. So how we make the address? Same as this. These two are similar. So maybe even we can put that together, but I didn't, no problem. Other than that is 0. So that's the ILU part, but you can extend that or expand that in any way you want. If you want more instructions, you can add that there. Not hard. So this is ILU. Any question about ILU? Okay, so we did fetch, decode, execution. This is very important. This is execution cycle that for any designing processor, you need to know that. And you need to do that. Without that, you can't make a processor to work because you need to fetch any instruction you want to execute and then decode to understand which instruction is that, which operation, which operand, and then do execution. ILU, we already designed ILU before. And after that, we put result in the memory or into registers in write back. So these steps are very important. In this computer, it's very simple. We do everything in one cycle, but sometimes this cycle becomes too big, and we can speed it up using other parallelism mechanism, like superscalar or pipeline that we're going to see soon, maybe next week. Okay, so let's go to, if you have any question about this, let me know. If not, we can go to next one. The next one is for memory. We are here. Memory access, read from memory for load instruction. And we are here we implemented just load, not the store. But you can do that store too. I'm going to tell you in your assignment which instructions you need to implement. Anyway, if you just have load, so ILU result that is showing the address, you are accessing that. Still, I am shifting that 2 bits to the right, dividing that by 4 to do addressing. The memory, this address is a byte address, but this data memory is actually word address in this computer. So we also have D memory. Same way that we defined instruction memory, we also have D memory. So same size actually. So we have something like that, registers 31 to 0, D memory 0 to 123. So again, is like a memory. Each of these is one register. This is least significant bit. This is most significant bit. Okay, so we have also this data memory. Okay, so this is the address. We access to this data memory, put it in a memory data. If the instruction is load, we get it from here. If the instruction is not load, it's probably R type or I type. In these two cases, the output gonna go from ILU result directly. We just like a bridge, have a bridge from the memory, we get it from ILU. Do you understand this part? Any question about that? How we get this memory data? Because this memory data is something important. We need to write it back into register files in the next step. So we fill it from memory or from ILU. Good? Okay. So the next part is write back. Because I need a space, let I clean this up. Yeah, I'm just going to put that here. So that's a write back. So write back is very simple. We just put whatever was inside mem data that coming from data memory or coming from ILU, we put it in a register destination. Easy. We have register files and RD showing the address of that destination that coming from from decoding. That's is actually happening if the opcode is R type or I type or a load word based on our design, and also is not 0. Yeah, you just can put that control to check everything okay. So that's write back, and then we add program counter. This is the very simple design of processor. I didn't write that completely because you're gonna do that with more details for your next assignment. If you have any question, let me know. It's gonna give you lots of ideas actually. When you design that, when you can run it, it's gonna give you lots of idea how computer works. I hope you do it properly, not copy everything from ChatGPT or any AI tools. Okay, so let's go to more details about different part of CPU. We already talked about combinational parts. We have adder, we have multiplexer, we have ILU. This part doesn't need any clock. We call them combinational elements. So for ILU, as you can see, we designed that last week or 2 weeks ago. We have operation that coming here. We have registers as an input and do operation and make output, sometimes make some other signals, like a 0, for example, or carry sometimes. We also have multiplexer. As we explained, this is not right to, we just connect 2 cable or 2 buses together. That's wrong, it's not working. So we need to have a multiplexer in this case, and multiplexer has one or multiple select. So this is mux. Mux, and this is select. Is get some input, like for example, in this case, as you can see, it's coming from program counter +1 or coming from program counter plus like immediate, for example, or something else, and go to new program counter. So we need to put 1 here. Also for here, we need to do that. If the instruction is memory instruction, we need to, this is select, another select, this is another select, like this is S0 is S1. And if is R type, it goes from ILU instead of coming from memory, data memory. Here also we need more multiplexer. So that's not correct. If you connect them together, it's not work. In the lab, probably you saw that. If you connect 2 cable with different data, it's not doing anything. It's just destroy the data. You need to have a control to let them. It's like a switching them, which one goes, which one not. So that's how multiplexer works in digital logic. We saw application of that a lot. As you can see in that example that I wrote here, we also, in that, the data coming from program counter +1 or the branch or jump. Any question about multiplexer? In these parts, I go faster because you already had in digital logic, so we don't need to waste time in that. For ILU, that's a single bit ILU that doing AND, OR, and add. This is AND, this is OR, this is add. And who specified this? Inside this, you have a small multiplexer that this opcode specify the output coming from which one as a result. So this is 1 bit. If you want to make it 4 bits or 16 bits, you're just gonna put them in a row like that. Of course, here you have a problem of timing, as we explained a couple of weeks, maybe 2 weeks ago, about ripple carry adder that has a problem. This has a ripple carry. This is a ripple carry adder. We call it RCA because the carry need to pass from one to the other, and that makes it very slow because the longest path, slowest path is very long, and that is make the design of this circuit very slow. But to solve that, we said we can use another type of adder that is carry look ahead adder. Look ahead. Why is eliminating that? This part of my laptop is not carry look ahead adder. CLA, we call it CLA, carry look ahead adder. So we are making kind of we are making actually these carries in ahead, you know, that's why it's called look ahead adder. So anyway, that works too. If you just put this, even though it's slow, but it still works. But you need to make the timing and clocks longer. Any question about this adder? We already had that. I just wanted to show everything in one page. About the memory. About the memory, we learn in digital logic that you can, to make 1 bit storage, you can use latch. Latch is a level sensitive, so it's based on the level sensitive. So working, but this has a timing issue. To fix that, we made flip-flop. Flip-flop is an edge triggered instead of level trigger. Is edge trigger. Doesn't matter is a rising or falling, but most of the time we use with rising. We can use 2 latches together to make flip-flop. So the flip-flop actually make 1 bit storage for us. How make registers? We just need to put them in a row, like for example, n of them together to make n-bit registers. So as you can see, we have clock for all of them, and we have a write enable, and also in and out. So pretty much we knew how it works. When the, for example, write is 0, register keep whatever was there. When it's 1, this gonna be ready to go in, but it's not gonna return till clock coming. When the clock coming, whatever was in this bus, this is the bus, n-bit bus, gonna go and sit and in the registers. So clock is very important. So reading the register, reading this register is combinational, but writing is sequential. Is very important. So reading is combinational, means when you put the address when you put the data, I mean, doesn't need to put data. Whatever is here, you just can read it. Is always is in the out part, in the data out. You can take it. So the reading is combinational. Writing is sequential. Writing, if even you put the data to write it here, it's not going to return by itself. First, this write need to be enabled. This need to be 1, as we mentioned here, and then clock coming. And the clock coming, that's going to get written inside. If we put these registers together in a 2D dimension, we're going to make register files. Designing these register files is this is a complex register files because it's a dual reader, but you need to make that inside with probably another circuit for that. But we're not going to design that here in this class. Anyway, that's the type of register files that you can put the address of registers that you want to read ready, and the address of register for writing here, and the output gonna get ready right away. So this is also reading is combinational. So in this example is 32 general purpose register. In RISC-V is 64 bits, but in our design was 32. But you can make whatever you want based on your things or whatever I asked in the question. I still didn't design that. I'm gonna take a look to see. And we're gonna do 2 read port and 1 write port, and and X0 is always 0 in RISC-V, and the clock writing is based on clock, but reading is combinational. Any question? You already talked about that a lot. Let's see if we have time. We just go about the storage. Okay, if this register file get bigger and bigger and bigger, become memory. But memory is not the dual. You just any point of that you want to access, you put the address here, and when you put the address here, you can read it right away. You don't need clock for reading. Reading is combinational, but writing is need clock. For writing, again, you put the address and also put the data in this bus ready, and the clock coming and it's gonna get written. You have memory read signal and memory write as a control signals. Okay, for synchronization, we're gonna talk about that next class. That's important, very important. Hopefully for your Verilog, you don't need that much synchronization because, yeah, you just put clock at the top and it's gonna be done by itself most of the time. Okay, any question? So see you Friday.
No, I love my 311. Let's go.